All right, good afternoon again. For those just joining us, my name is Walt Engelund. I'm the Director of Space Technology and Exploration here at NASA Langley. We have had an exceptional lineup of speakers so far today commemorating the NASA Viking lander, successfully touching down 40 years ago to the day on the Martian surface. That moment, along with many other historical milestones before it, have allowed us to move forward on our journey to Mars. One day soon, we will be able to complete another milestone in the nation's history by sending humans to the red planet for the very first time. So we now have a panel of speakers here with us that will talk about the present and future state of NASA's journey to Mars. Joining us for our panel discussion this afternoon is Greg Williams, who is the NASA Deputy Associate Administrator for Policy and Plans and the Human Exploration and Operations Mission Directorate. Greg helps NASA outline the future course of human exploration for NASA. We have Dr. Jim Green, Director of Planetary Science Division and NASA's Science Mission Directorate. Jim oversees and advocates NASA's planetary science research and operations. Mr. Steve Jurczyk, NASA's Associate Administrator for Space Technology and former Director here at NASA Langley Research Center. Steve plays a leading role in the management of NASA's future missions and technology development. Dr. Stofan, NASA Chief Scientist. We heard from her this morning. She was our keynote speaker. She's going to come back up and join us as a panel member. She serves as NASA's principal advisor to the NASA Administrator, Charlie Bolden, on the agency's science programs, science-related strategic planning, and investments. And last but not least, a young face of the Mars exploration community. You'll hear from Melissa Traynor. Melissa is a research space scientist in the Planetary Environments Lab at NASA's Goddard Spaceflight Center. Melissa is well-versed in the understanding of planetary atmospheres and offers an early career perspective, someone who will carry the torch soon forward with our Mars exploration journey. So now I'd like to introduce our first panelist, Greg Williams. Greg currently serves as the Deputy AA for Policy and Plans in NASA's Human Exploration and Operations Mission Directorate. He's responsible for assisting the Associate Administrator influencing and responding to the internal and external policy affecting human spaceflight programs. Before joining the Human Exploration Operations Mission Directorate, Williams served as the Deputy Director for Strategic Integration in NASA's Science Mission Directorate. He started at NASA as a presidential management intern in the Office of Space Station at NASA headquarters, and he led strategic planning and communications activities for the Earth observation systems. Greg, welcome back to Langley. The floor is yours.
All right, good afternoon. It has been a tremendous privilege to be here throughout the day and to hear from the Vikings of old and how all this transpired. It strikes me as I came to work at NASA with a lot of folks who were ending their careers after a long time with Apollo, that the Apollo crowd and the Viking crowd had one very important thing in common, which was that they just closed the doors and shut out all those who said it couldn't be done. And the evidence of all that is well represented today. I'd like to follow a little bit on the early discussion that Dr. Stofan gave us this morning about the journey to Mars and where we're headed, and looking forward about the goals of getting humans to Mars. And so we'll start with that. Today you saw this chart this morning, and Dr. Stofan very eloquently described the challenges that are ongoing in each of those areas, having to do with EDL, having to do with long duration human spaceflight. These are all challenges I want to report that we are taking on. For every one of these challenges that describe how hard Mars is, there's something that we're doing. There's an active program ongoing to identify, analyze, understand, mitigate, and even retire those risks. And you're going to hear from Steve Jurczyk a little bit later, who's providing the technology part of that puzzle, even as our organization in human spaceflight provides some of the research on the human element associated with those. But what I wanted to do is report a little bit about the strategy we're undertaking to take on this journey to Mars and some of the real progress we're making around the nation today to make that happen. You saw this in Dr. Stofan's pitch this morning. I have a love-hate relationship with this chart. It's a great one to make fun of. It's commonly referred to around the office as the squid chart. because our strategy does indeed involve a giant squid attack on Mars. It also has a great sort of planetary defense aspect of it for you if you're a Martian or planetary scientist. Mars, having lost its atmosphere, is now attempting to steal out of Earth, and they must be stopped. And so that's the basic motivation. We need to get there in order to make that happen. The thing that's on this chart that wasn't on the one you saw earlier this morning is the row across the bottom, and that's what I want to focus on briefly, and Ellen alluded to this morning. There is a strategy involved in this journey to Mars. It is, in fact, a journey. It's going to take a long time. It's going to take a lot of doing. We have to move from today's Earth-reliant frame of operations, represented by the International Space Station today, with mission durations that are on the order of 6 to 12 months, and return times are measured in hours. If we have a problem on board the International Space Station, we can get the crew on board a Soyuz that's attached there and bring them home in a matter of a couple of hours. That's an important capability and one that gives us confidence about the program. Haven't had to do that in the 15 years of continuous operation on the ISS, but that option is available to us. The ISS is really, as Elle said this morning, the cornerstone of exploration. It's the research we're conducting on ISS, both in the Human Research Program and in technology development, that is going to get us to Mars. The environmental control and life support system we're going to use at Mars will be tested first on the ISS. But nevertheless, we're operating in this Earth-reliant frame of operations. Where we want to get to, on the far right, is an Earth-independent frame of operations, where mission durations are measured in years and return times are measured in months to a year. As you can imagine, that's an entirely different operating regime. It requires a great deal more autonomy, a great deal more advanced planning, very reliable communications, very reliable systems, because you can't, logistical resupply is a tremendous challenge in that environment. So for all of those reasons and more, this Earth-reliant frame of operations is quite a challenge. So how are we going to get from an Earth-reliant frame to an Earth-independent frame of operations? We're going to exploit the advantages of having this large natural satellite around the Earth, and we're going to use that and the stable gravitational environments that it offers to be a proving ground where we can test out automated rendezvous and docking and in-space propulsion and laser communications and all the things that we're going to need to successfully operate in an Earth-independent frame. And so in the decade of the 20s, we're going to be in this proving ground of cislunar space, the volume of space around the moon. And that's where SLS and Orion are going to operate, again, for most of the 20s. The idea is that by the end of the 2020s, we'll be able to conduct a shakedown cruise, if you will, that will move from demonstrating those systems and operational techniques to validating the readiness of those systems and those techniques for beyond Earth-Moon system exploration. In other words, exploration for the long voyage to Mars. And so this proving ground regime is where we'll be in the 2020s. In order to get there, of course, we're going to use the Space Launch System. I've put a comparison chart in here for you to look at with Atlas and Falcon on the one side and the SLS on the other. The Block 1 SLS, the 70 metric ton SLS, will launch first in November of 2018. We'll move from there to a Block 2, a Block 1B, which adds the exploration upper stage, which will get us to 105 metric tons to LEO. We'll fly that first in 2021, and then we'll use that system for much of the proving ground operations. And then with the addition of advanced boosters, we'll be able to progress to 130 metric ton capability, and that's when they'll really take us, have the sufficient throw weight to take us to Mars. And as you can see, we'll have both a crewed version and a cargo variant, as you can see on the far right with the large, I think that's actually a 10 meter fairing. 8.5 to 10 meter fairing will allow us to loft significant cargo capability to Mars, with the idea of our being able then to pre and place assets both in Mars orbit and on the surface in advance of human expeditions. So you've seen the view graph version. I want to show you now that we're actually making real progress on this. You'll see some efficient concept art here, but then it's going to dive into the actual hardware that's being developed for the SLS and Orion system. Orion is designed to be have a 21-day capability for a crew, but actually a 1,000-day capability in terms of its ability to survive in space if you add consumables to it. This is the Orion crew capsule being unloaded at Kennedy Space Center. This is the pressure vessel for the EM-1 mission that will fly in 2018. The Orion service module is being built by the European Space Agency. We've actually brought an international partner into the critical path of our program. We want the exploration program to be international in nature. These are the assembly platforms that go in the iconic vertical assembly building where we can process the SLS with Orion on top of it. There are 10 of these platforms. We are now halfway through installation. 5 of them have been installed, with 5 more to go. This is a solid rocket booster assembly. We fired the solid rocket booster for SLS a couple of weeks ago. The next time it fires will be when we launch the SLS in 2018. These are the RS-25s that we use as space shuttle main engines. We've got 16 of those that we can use for the first 4 SLS missions. We test fired them and run them with SLS flight profiles and with SLS controllers and mission durations, and so they're ready to go. As you can see, we're well underway with the first step of the journey to Mars, which is to build the launch vehicle and the crew exploration vehicle that is going to take us into the proving ground of cislunar space. These operations are going very well. It's always a challenge in any major development program, but I think we're over the large part of it. Almost all the pieces that we need to assemble Orion are at the Cape, and so they'll spend the next year assembling all that hardware onto the vehicle. The demonstration welds for the SLS tank engine core stage have all been accomplished, and we're now starting to load flight hardware into the vertical assembly center. If you've never got a chance to, if you've ever been to a chute assembly facility, it's really quite an operation. It's 46 acres under one roof. We have in there the tallest vertical welding tool in the world, 135 feet high. It kind of operates like in the inverse of a Pez dispenser, right? You take a 15-foot tall, a 15-foot wide section of tank, you load it in, you jack it up, you bring the next one in, you set it down, you weld it, you raise those up, bring the next 15-foot section in, set those down, weld it, and you do that 5 times, and then you've got a tank section, you've got a tank for the SLS, and you roll that out. And those operations are underway now, and will be for the next 10 months or a year or so. Then the next piece, once you have a launch vehicle and a crew capsule, is you then need in-space propulsion to be able to take you where you want to go in this volume of space around the moon and eventually to Mars. Steve Jurczyk's organization is developing the solar electric propulsion, and we're going to demonstrate that capability in the asteroid redirect mission. I have just a cartoon of it here, showing that what we intend to do is to pluck a large boulder, about a 6 meter up to 20 ton boulder, off of a larger asteroid, and redirect it to the stable orbit around the moon, and then we will visit it with SLS and Orion, and crews will conduct EVA operations out of Orion and sample the asteroid and bring those samples back to Earth. This affords us a number of opportunities to advance a number of our objectives in cislunar space in this proving ground era, this proving ground region, of techniques we're going to need in order to be able to affect the journey to Mars. We'll be able to do the automated rendezvous and docking. We'll be able to do the EVA out of Orion. We'll be able to demonstrate that we can encounter and manipulate a large mass, which we'll have to be able to do. And so this robotic mission is planned for the end of 2021, and then in 2026 we will. It'll take that long to get the asteroid back into to lunar orbit, and then we will in 2026 we'll have the crewed mission with Orion to visit the asteroid and bring that material back, and then we will be able to repurpose that spacecraft for other exploration objectives. Then once we have in-space propulsion, begin to have a handle on that, the next stage is then habitation capability in cislunar space. We want this habitation capability in cislunar space in order to be able to practice again, demonstrate that we can do long duration missions in deep space, but then once we've done that, we don't want to just abandon this hardware. It will then become the transit vehicle we will use to get to Mars. And so we have a number of activities ongoing to develop this habitation capability. We have international partners that are interested. We have capability at the centers. And then we also have a rising number of commercial enterprises that want to be involved in the space business. And so we have done issued what we call the next step, next space technologies for exploration partnerships solicitation, and have selected 4 potential providers to demonstrate their concepts. This is a little bit different than just letting a study contract, in that we have required each of these companies to bring money to the table in terms of capability they're going to provide on their own dime. We want to do this as a partnership for 2 reasons. One, we want, as one byproduct of this, to have these commercial companies gain experience with and be able to then subsequently invest in their own private sector systems in low Earth orbit, such that after the end of the space station's life, that there will be companies who can then put space station-like capabilities in low Earth orbit and mature that market, so that when NASA goes off into deep space, there'll be a commercial capability in low Earth orbit to be able to meet a private sector demand for that activity. And so we've pursued this habitation capability with a co-investment construct. We have completed the phase 1 of that activity. We're now moving into phase 2. We hope to be able to select and either among these vendors or perhaps on-ramp some new ones in the early August timeframe. And then they'll spend the next year and a half maturing the next level of detail in their habitation concepts, aiming towards, in 2018, a ground-based engineering model that they will be able to then prove out those concepts. And then with those, we'll establish a reference architecture, bring out our international partners, see what they want to contribute, and then by 2020, be able to make a decision on the actual hardware we will fly in the mid-2020s in cislunar space with SLS and Orion. So we really are off and running on this proving ground set of capabilities. I'll end with this. Once we have established and again validated in the proving ground of cislunar space by the end of the 2020s that we can that we're ready, that we know enough, we have enough experience in technology and operational techniques to be able to leave the Earth-Moon system, we will then, by the mid-2030s, accomplish the goal that Ellen put up there this morning, that the President gave us, to visit Mars with humans, the Mars system, by the mid-2030s, and then eventually the Martian surface after that. I'll end with this image. I like it because this is an astronaut standing on Phobos. The realistic part of this is that Phobos and Mars are in their proper relative sizes. That is, if you were standing on Phobos, this is what Mars would look like to you. It would be that big in your field of view. And we believe that Phobos could be a very compelling destination as for this objective of humans to the Mars system in the mid-2030s. And with that, I'll turn it over to Jim Green, who knows a lot more about Phobos than probably anybody in the room. Thank you.
All right, let me reintroduce our next speaker, Dr. Jim Green, who was with us earlier this morning. For those of you who weren't, let me tell you a little bit about Jim. I don't need to do this. Jim's the Director of Planetary Science at NASA headquarters. All right, so Jim, tell us how the science robotic world is going to integrate with the human exploration world and make all this a reality.
Thank you very much, Walt. Okay, indeed, NASA has had an aggressive program of visiting Mars and learning about the science of Mars, as I discussed earlier today. These are the missions that NASA has launched, mostly successful, although we've had some failures along the way. Our last mission, MAVEN, which has been in orbit now for more than a year and a half, is really studying the solar-wind interaction with Mars and understanding how coronal mass ejections and particles that get accelerated actually impact Mars and contribute to the radiation environment that also must be considered. Our next major step, as I mentioned earlier today, is indeed the launch of InSight, a tremendously important mission for us to be able to study Mars as a planet and with major feed forward for human exploration. It indeed will look at the seismology, the heat flow of the planet, and also potentially have the ability to measure what that environment is like for human exploration. And then finally in 2020 is the Mars rover. It's based on a similar architecture that we have flown with Curiosity. But this is a very important mission. It actually, in many ways, is a follow-up from the Vikings. It has the opportunity to sit down in a geologically diverse environment, core rock, and then our plan in the next decade, in the 2020s, is to bring back those samples. The samples are about the size of a piece of chalk. They'll be encased in a tube for which the accumulation of those tubes will be laid on the ground. In the 2020s, we'll then have a fetch rover to be able to do what I call follow the brick road, yellow brick road, and that is land and follow the path perhaps the Mars 2020 rover took to be able to then pick up the right set of tubes. We'll catalog each one of those when we take the observations such that when we bring those tubes back, we'll know the provenience, we'll know the regions on Mars that they were taken. And then we will have a Mars ascent vehicle to return those samples. The reason that's so important, of course, is it enables us to bring the right environment back, put it in our laboratories to study Mars, resolve the question on whether there is life on Mars or not. In addition to the rock samples, we'll also have regolith and soil samples. We'll be able to perform the labeled release experiment in our own laboratories and understand really what the physics is behind the observations that were made by the label release experiment while it sat on Mars and performed its job. Having samples back from Mars really is a gift that keeps on giving. If you can imagine walking in laboratories where a huge set of equipment that examines in great detail the elemental composition of the rocks, the mineralogy, how water may have modified those, creating the appropriate minerals that you see, looking for minerals on Mars that we don't even have on Earth. And these are the kind of things that can only be accomplished in major ways if we bring those samples back. Bringing those samples back also is in line with human exploration in the sense that we'll have to have a Mars ascent vehicle. We'll have to be able to erect a rocket, acquire those samples, and then return those samples by injecting them into perhaps an orbit around Mars with another vehicle that will capture and bring them back. Looking at how human exploration is defining the next several stages, the proving ground being in the lunar area could be a very important location for us to return those samples to. for which then humans can be able to acquire those samples and then bring them back as they re-enter the atmosphere and come back home from that. Or we'll be able to return those samples by directly bringing them back through the atmosphere, as we have done with several missions such as Genesis and Stardust. So we have many options, many approaches. Many of these connect really very strongly with human exploration. As I also mentioned today, there's a tremendous amount of feed forward in our science. This is absolutely a central part of our program, is to study Mars and the environment to the point where we can leverage and use the resources. In the upper right-hand corner is these reoccurring slope lineae that we see. This particular picture is actually made up of images from each season, all 4 seasons. And as you can see, in the winter, spring, summer, long lines, fall, and then back to winter, the reoccurring slope lineae do indeed appear during the summer environment. We need to understand much more about where this water is coming from. Indeed, we have found what we believe is a buried ice cap on Mars. Mars has, over time, changed its obliquity. That means its inclination to its orbit plane, allowing then a different diurnal cycle on Mars, depositing ice through its seasons in different locations. And this particular location could indeed have a vast resources of water. So our robotic missions have really pioneered several of these approaches. As Steve will talk about, I'm sure, much more extensively, there's a lot of feed forward in the engineering. The feed forward in the engineering is happening today with our robotic missions, as we're also planning how we can extend this to our future missions. Entry, descent, and landing for the Mars 2020 mission will be very similar to what we did with Curiosity. But make no mistake, just because we did it once doesn't mean it's going to be successful the second time. We have to do the due diligence necessary for us to be able to ensure that we can do everything humanly possible as we go through each of the phases in testing, entry, descent, and landing. We have some great data from Curiosity. Implementing what we know on the next mission is critical. Our engineers and our scientists form those teams that then can work on the next mission to make that success occur again. We have to be able to continue the investment at our centers, in our people. This is a critical thing that has to continue on, that allows us to transfer the knowledge so important, so necessary for us to be successful in the future. Success breeds success, and how we take advantage of that is through the investment in our people and our engineers. NASA does that better than any other part of the federal government, in my opinion. So I think with that, let me turn it over to Steve Jurczyk. Excuse me. Steve?
Steve Jurczyk, Associate Administrator for Space Technology, the guy that's going to develop the technology that's going to get us all to Mars. Steve.
Thank you, Walt. Hey, thanks, Walt. So it's really good to be back at the Mother Center, NASA Langley. I've been with NASA 28 years, and I've been at Langley 23 of the 28. So this will be home always to me. So I was here for the 30th anniversary, Viking 30th anniversary. Oh, thank you. And I remember a couple of things about the 30th. I was a deputy center director at the time. One was Tabak. So it was the last time I ever saw somebody give a presentation with viewfoils at the Viking 30th. We wheeled the viewgraph projector up to the front of the old Reed Center, and I think, was presenting the viewfoils from the Viking CDR. And it was awesome. It was awesome. I just ate it up. And then another thing was what Tom talked about earlier, which was, and it stuck with me, which was resisting the temptation to land at the pre-selected landing site because of the pressure of July 4th. Right? There was huge pressure. It was a big deal, going to land on July 4th, 1976, huge pressure. And the team said, it's not the right thing to do. It's the wrong thing for mission success. We're not going to let the political and the public pressure do that. And that just stuck with me, particularly since now I'm in Washington. And that's even more important now I'm in Washington. Yeah. So that also stuck with me. And then one last thing, and then I'll get to my presentation, is with Gentry Lee, I was the co-chair of the EDL Standing Review Board for Curiosity, for MSL. And I had the privilege to, Gentry asked me, I had the privilege to be on the Landing Site Risk Assessment Committee with Tom for Curiosity. And we had of all the landing sites, of all the 4 landing sites we were considering, we had stereo imagery from high-rise and digital elevation maps, right? And so I looked at Tom and I said, Tom, how'd you guys do this for Viking? What did you have? And he goes, well, the risk assessment was easy. We had nothing. So every site was as risky as any other site. And that's also stuck with me too. So we've come a long way. I guess now I should get into my presentation. Okay, so first I want to talk about some of the guiding principles we have in developing space technology. One is we are mission driven. Okay, the number one measure in my organization is, are we delivering technologies that are enabling human exploration of the solar system and enabling the next generation of science missions, as well as the commercial space enterprise. If we're not doing that, we're failing, right? However, we do also push technology. 90% of what we do on this technology pipeline behind me is mid to higher TRL. It has a mission pull. We know what we need it for mission for propulsion, in-space propulsion or ISRU or whatever. But 10% is push. We know it has an application. We know we're going to need it. Nobody on the mission side is jumping up and down and asking for it, but we're going to push a little bit. And that's about 10%. So you want to have a spectrum, mostly in the mid and higher TRLs, but some in the low. The other thing we want to do is engage the broadest possible participation in developing technologies and getting to the systems capabilities we need. So working with the NASA centers, with universities, with small businesses, large businesses, traditional space, new space, you name it. We are working with the broadest set of, and we're doing things like prizes and challenges to even draw in the not usual suspects. The person who won the astronaut suit glove challenge was literally just about a garage inventor. And he brought the best solution to the table. And so that broad participation. Partnerships are also key. You'll see on the last chart I have all the things that we're test flying and demonstrating in space are partnered for launch, are partnered because we're hosting the payload, are partnered with HEO and SMD. I mean, it's, we're trying to do things effectively and efficiently. So partnerships are really key. And then, we manage these like projects, right? They have requirements, they have schedules, milestones, beginning, middle, end. We do not have level of effort activities. We need to deliver the technologies that are needed to enable human exploration and robotic exploration. So those are just kind of the things that guide us and drive us. And Ellen showed this chart. I could spend a really lot of time on this chart. I will spend some time. So I break it down in, we need to get there, we need to land there, and we need to live and work on the surface of Mars, right? Lots of things in getting there. So Ellen and Greg mentioned what he is doing in the Human Research Program, right? Human health and performance, radiation, microgravity environment, really tough challenge. Making a lot of progress on International Space Station. A really lot of progress on understanding how the countermeasures that are going to be necessary to keep crew healthy and productive. Next thing is environmental control and life support systems. They work on station. But they break a lot, and we need higher performance systems. I don't not necessarily think we need to close the loop on our environmental control and life support, but we need to get a lot better, and we need to get the reliability up for what we call Mars class ECLSS, and that's going to be really important for transit and on the surface. Let's see, we talked about rendezvous and proximity operations, developing technologies that I'll talk about on the next chart there. And then in-space propulsion technology, right? So we have chemical, right? We got I would call high power solar electric, very high power electric, including nuclear electric, and nuclear thermal. Right, those are our options. Like Greg mentioned, we're going to be demonstrating higher power solar electric, but we're also investing in what I'll call very high power electric propulsion in actually HUMD advanced exploration systems, as well as nuclear thermal. So in-space propulsion to for efficient transportation of cargo using high ISP solar electric, as well as maybe some rapid transit type technologies. Okay, so I think I could summarize landing there with what Rob Manning said earlier, if you saw his presentation. So I thought Rob summed it up really well. And they used everybody used all the good lines, 7 minutes of terror, Mars has a poor excuse for an atmosphere, all that, right? And it's true. And you just look at the history of, there's a chart that shows everybody that's attempted to go and land on Mars and the successes around the world globally and the successes and the failures, and you can see from that chart how hard it is to land on Mars, which makes what the Viking guys did in 1976 super, super impressive. So we still use the 70-degree sphere cone plan form for the entry vehicle. We still use the disc gap band supersonic parachute. JPL's been really good at innovating the terminal ascent and landing piece, airbags hard, and then sky crane. But we're kind of run that technology out so that we could land about 1 metric ton on the surface. I think Curiosity was about 970 kilograms, and that's about all we can do. I think we scaled the parachute up to 21.5 meters. That's all we can do. So we're going to need new technologies, and a couple that are common to all architectures, like Rob mentioned, are supersonic retropropulsion. We need to prove out supersonic retropropulsion on Mars, and autonomous landing and hazard avoidance technology and precision landing technology. I'll talk about what we're doing there later. And then there's a whole bunch of systems we need on the surface, including, Greg talked about transhabitation, but we're going to need habitation on the surface. We're going to need surface power systems to power everything, including the ISRU, suits, robotics and autonomy to work with the astronauts and maybe to tend and maintain the systems when we don't have crew on the surface. And then we're going to need ISRU and everything from producing fuel, water, breathable oxygen, food, building materials, using 3D printing, right? We need to look at living off the land as much as we possibly can to try to minimize this incredible logistics train that we're going to have for human exploration of Mars. So really large challenges, and we are doing a lot to meet those right now. So these are just the set of technology demonstration missions that we have. And like I said, they're all partnered internally and externally to the agency. I'll highlight just a few of these, and then I'm going to show a video that kind of gives you a visual of a lot of these and some more. So we're developing a mercury ion clock, deep space atomic clock, for precision navigation. Basically to enable one-way ranging, navigation using one-way ranging to simplify operations. It drifts 1 microsecond every 10 years. And it's being developed at JPL and will be flown March of next year. We're doing satellite servicing. We're going to refuel a government satellite in low Earth orbit. But on that mission, we're developing the sensors for Orion, for rendezvous and proximity operations. We're also developing the robotics for the asteroid redirect robotic mission. So that technology will feed forward in a couple of things, a couple of capabilities that we need. High power solar electric propulsion on ARM. We've done all the what I call the engineering development in that. We just led a contract to develop the flight hardware. So as well as we developed and ground tested 2 large deployable solar arrays to power the solar electric propulsion. And then deep space optical comm. We're going to increase the bandwidth of communications using optical communications by an order of magnitude to the 200 to 300 megabit per second range. And incredible challenge there with the laser transmitter, the stability and control of the pointing system, and the sensitivity of the receiver system needed to do deep space optical communications and enable that high bandwidth comm. So just some of the things we have coming up. So lots of things to accomplish and fly and between over the next 7, 8, 9, 10 years. And with that, I want to play a video which will kind of give you a visual of all this stuff that we're doing, all this great tech that we're doing.
5, 4, 3, 2, 1, and liftoff at The dawn of Orion and
Yes,
a
I got
new
to go to
era of
EFT1.
American
It was a
space
great day.
exploration.
It was my wife's first launch in 28 years. I finally got to go to. So just to wrap up with some things we're doing on Mars 2020. So kind of three things. One is entry, descent, and landing instrumentation. So we. Not to interrupt the president, but so I got to cut off Obama. So three things on Mars 2020. First, entry, descent, and landing instrumentation. We flew some pressure measurements, temperature measurements, recession sensors on Curiosity, and we're going to fly improved measurements on the heat shield for 20, and then we're going to have some back shell measurements too. Second thing is MOXIE, the Mars Oxygen Institute Resource Utilization Experiment. We're going to generate oxygen from atmospheric CO2 at very small scales. It's a proof of concept. It's flying as an instrument on the rover. And then terrain relative navigation. So Rob talked about flying blind. Actually, on 2020, we're not going to fly blind. Using cameras and digital elevation maps, we're going to essentially, detect where we're going to land, see if we're headed to a hazard, and then if we are, just divert and go to a better side. So it's not closed loop control, but it's more hazard avoidance, and that came out of the All-Hat project and some of the suborbital flight testing that we did. So three things that we're, partnered with on 2020 that we're kind of infusing to move forward. And with that, I'll stop and just thank you for the opportunity to speak here today. Appreciate it.
right, please join me in welcoming back Dr. Alan Stofan, NASA's Chief Scientist.
Thank you. Yep. Okay, so we've heard about how we're going to do it, the rocket we need, the capsule for humans, the habitation system. We've heard about the great science that can be done with humans on Mars, and we've heard about the technologies we need to make this happen. But there's something critical here, and that's the actual people that we're trying to get to Mars. It's those humans, and I wanted to step back and remind you again of why do we need people? Why can't we do this with robots? And for one thing, just think about the Opportunity rover. It's been on the surface now for over a decade, which is completely amazing, returning science that whole time. But in that time, it's gone a little over 26 miles. So a marathon. Now, I can't do a marathon probably even in a day, but there are people who can move that far in a day. So think about what a human brings to the equation: mobility, flexibility, creativity. And you know, I'm biased. I'm a field geologist. I go out and study volcanoes around the world, and I really have this bias that it's going to take a trained field geologist out there on the surface of Mars to really accomplish the science that we want to accomplish on Mars. So our crews every day up on the International Space Station, as I said earlier today, are working on how do we get that human health element? How do we get humans to stay healthy for that 7 to 8 month journey to Mars that we're stuck with right now until Steve can get us nuclear thermal propulsion and get us there a lot faster? And we know from our experience on the space station that we can do this, but we are also well aware of the numerous health effects. For example, probably the one you've heard the most about, bone density loss and muscle wasting. Well, it turns out with the current protocols we're using on the ISS with the astronauts, if they exercise about an hour and a half a day, and some of my astronauts friends tell me that when everyone on Earth knows if you're going to exercise or not that day, you actually do tend to exercise. Unlike me, no one knows if I do or not, so I can get away with it. But for the astronauts, if they do that much exercise every day, most of them can return to Earth with about the same bone density and muscle strength as they left with. So that's usually for our 6-month cruise. Nutrition. Obviously, as we've learned increasingly over the last 20 years, and this has certainly informed our human research program also at NASA, a lot of how we stay healthy has to do with what we put into our bodies. And not surprisingly, again, for those of us in this room who worry about these things, you know, if you eat a healthy, balanced diet, you don't eat too much salt, those things that keep us healthy here on Earth actually keep our astronauts healthier in space too. But of course, then that provides problems. How do we ensure that astronauts on that journey to Mars can have fresh food? So just in the past year, we've been running an experiment called Veggie, where we grew lettuce on the space station. The astronauts ate it. They said it tasted fine. We've been growing flowers. Okay, why flowers? Well, think about the fact that you need the food to come to fruit or flower as rapidly as possible in space, with using as little water as possible. So we're doing things to really push what we understand about plant biology, translate that into how plants behave in microgravity, to really understand better how we can grow plants in space. And think about it also from a plant point of view. Think of a wheat plant. You know, that plant, it's got that big, huge, tall stalk to hold up that seed head due to gravity on Earth. The plant has evolved in the presence of wind and rain, storms. Up in space, we don't have any of those things. So that's the other thing our researchers are thinking about. What is a space plant that can feed astronauts on a rapid basis? What does that plant look like? And how can we work towards that goal so that we can keep astronauts with fresh food on that journey to Mars? Medical kits and devices. I was at a conference last week, the ISS Research and Development Conference, talking with Dr. Eric Topol out in California, who's an expert on this next generation of medical devices. And for those of us who might wear exercise bands, you know, maybe you don't have a lot of confidence. I tell you, these devices that are the next generation are amazing. Instruments that can do a sonogram of your heart that just plug in to a mobile phone. Bands that actually can measure blood sugar, giving you constant readings of blood pressure, doing EKGs, all devices on the size of a smartphone. So where medicine is going here on Earth actually has a lot of synergies with this whole issue of how do we have devices in a small mass area as possible. But we really think about it, NASA and the Human Research Program. What are those devices we need to take with us? How do we get shelf-stable medicines that will last on 3-year journey to Mars? Ocular health. The astronauts have a syndrome where some astronauts come back with some visual impairment. There's some thought that it might be caused in the rise in intracranial pressure. You go into space, fluids migrate around your body. There's been a thought that the rise in intracranial pressure could put pressure on your optic nerve and do some damage. Well, we're not sure. People have done head-down tilt table tests, actually taken people up in microgravity, the Vomit Comet flights, and it turns out our early data seems to suggest the intracranial pressure goes up and then it actually falls. So what is causing the ocular problems? We don't know. We're working on it every day on the ISS. Radiation is obviously one of our key issues because once we get out of the Earth's magnetic field, out in the vicinity of the moon, on the way to Mars, the astronauts are being subjected to both cosmic radiation, solar radiation. Solar radiation we can do a fairly good job of shielding against. They do a lot of work on that right here at the Langley Space Center. Cosmic radiation, a lot harder to shield against, so we're trying to understand why are some people better repairers of radiation damage at the cellular level, at the genetic level than other people. So there's a lot of research to be done between now and when we're ready to send astronauts to Mars. Now also realize that most of the crews go up for 6 months or less, so we're getting a really good database of all these health effects, all the countermeasures for about a 6-month time period. But again, that mission to Mars is more like 2 to 3 years. So just this past year, you're probably aware, it got a little bit of press. We had 2 astronauts up on the space station for a year, Scott Kelly and Mikhail Kornienko. I love some of the data from this. 459 total samples collected from them during that time period, and you can read exactly what those samples were. Joint U.S.-Russian investigations on Scott and Mikhail and these longer duration effects going from that 6-month to the 1-year increment. And then, of course, we had the added amazing benefit that Scott Kelly just happened to have an identical twin. Because it actually turns out, from loss of immune system function in space to we want to look at this visual thing, it turns out a lot of these changes are actually taking place down at the genetic level, your epigenetics. It's sort of, think of it as sort of the grammar that controls the words. The words are your genes. The epigenetics is sort of the grammar of how they behave. So it turns out a lot of these changes in microgravity are taking place down at that epigenetic level. So actually having a control here on Earth that we can be comparing those results on on Scott up in space to Mark on the ground has been extremely useful. I love this video because to a lot of us, I think the ISS, we see those photos from the outside and we forget what an amazing laboratory it is from the inside. And you could see from freezers where we keep samples, from the 3D printer we have, furnace where we do combustion experiments, incubators, microscopes. We just took last year and this year we've taken genetic analyzers that can actually do genetic analysis. And then of course we have the people who are actually doing the work, the astronauts. So all of this is getting us to this point of getting humans ready to send, to go on that long journey to Mars. And again, by the 2030s, when we get our rocket ready, we get the Orion capsule tested, we get the habitation vehicle ready, we understand where we want to land, we'll be ready on the human side to get astronauts to Mars healthy, ready to work, and then get them healthy back to the Earth again. Thank you.
Thank you, Ellen. And last but certainly not least, I want to introduce a fresh young face to the Mars exploration community, Dr. Melissa Traynor. We thought it would be a good idea to have somebody who could share a unique perspective from a young person with all these veterans of Mars exploration. So, Melissa, welcome.
Thank you. Okay, so thank you, everybody. It's really an honor to be invited. Thanks to Walt, Engelund, and Joel Levine for having me here. It's quite a charge to be given to represent a whole generation of new Mars scientists, and I'm honored to be here. One thing I wanted to say, since I had that introduction as being the fresh face, so to speak, and the young person, I have to confess that I don't have, I don't have any personal stories of my experience of the Viking landing. I was a little presentient at the time, so I can't tell any of those stories. Sometimes people don't like me to point that out, but like I said, that was my charge. But if we do add up the years in Mars years and age of the Viking appropriately, then they're only 20, and so then I'm more senior, so it's okay. Anyway, so one thing I wanted to talk about was, again, part of what is it that brings us to Mars? What is it that brought us to Mars with Viking 40 years ago? And what is sort of the state of Mars science and where are we at today and looking forward, kind of with this idea of where are we going? We've got all these great descriptions of the new technologies and the new missions and bringing humans to Mars. And I just wanted to take a moment to give a perspective on the science. And so this, to me, this is the driving question, right? Is there life on Mars? It was the driving question bringing Viking landers there, and I still think it's the driving question today. I think there's a lot of nuances that feed into this question and to understanding Mars and also just life in general in the solar system and how our own planet came to be. And what's really fantastic about this is it's really brought us to, as we're exploring Mars and trying to get at this question, pushing the boundaries of the knowledge of all sorts of fields, right? Of climate science, as we try to figure out what was the environment of Mars like in the past and how did it evolve to today. Geology, of course, we got to hear a lot about the geology of Mars, the mineralogy, the clues that gives us to Mars' past. And in addition to that, chemistry and microbiology and biochemistry and biology and all of these amazing sciences that help us understand Mars as a system. And that also teaches us, again, a lot about our own planet and what that means for us. So I actually think it's great. It may be great that we don't know the answer to this question yet, because we've learned so much on the way. Okay, so again, did life ever exist on Mars? We talked a little about Earth's history, and we don't really know how life got started on Earth. We know it's here. It's our current data point of 1. But we have some constraints just based on what we've understood about the planet, about around the time that life started to have an effect on the environment in a way that we can see in the geologic record. And again, what we've been learning about Mars from exploring the atmosphere and the changes that we can see in the composition and in little clues like the isotopes in the atmosphere or in the water is that at the time that life was evolving on Earth, something like 3 billion years ago, Mars could have looked a lot like this, right? And they look pretty similar if you get, the right artist's conception. We've got oceans on the planet. If we have a warm enough climate, it doesn't have to be super hot, but if it's warm enough to support liquid water, then maybe at that same time, I think it's this fundamental question to question, well, what was going on next door? Is there any reason that what was happening on the Earth at that time couldn't have been happening on Mars if the conditions were right? And that's been a big driver. So whether we're looking for current life, extant life on Mars, or whether we're just looking for evidence that there ever was life on Mars, I think that's either way, I think that would be a phenomenal discovery and a way for us to understand, in part, a lot about what it was like on early Earth and how life evolved on Earth. I think as mentioned earlier, was there 2 independent genesis, or was there some transfer? Maybe life started on Mars and moved to Earth. These are things that we're still trying to understand and we'll still keep looking for. So one big thing, and we have heard a lot about this today, is just how much more we have learned about Mars and how that is helping us continue to refine our exploration approach and how we're going after learning the answer to some more of these questions. So For example, we talked a little bit about the surface of Mars. So far, our exploration of Mars has been superficial. So we have, imaged the surface from orbit. We have learned the mineralogy. We have these fantastic geologic maps, and we've landed, and we've scooped, and we've even started drilling, and that's amazing. But we're still talking about exploring this much of the planet. I forget exactly how deep those drill holes are, right? And we know, listening to Dr. Boston and thinking about all the different environments that there could be on Mars, there could be so much more under the surface. And so looking ahead, for example, with the ExoMars rover, one big goal is to start accessing that area below. And when we do that, will we be getting away from some of the surface conditions that we have since learned might make it difficult for us to find evidence of possibly extant life. So things like the organics that could have been present, we know that they're delivered by meteorites, but it turns out they're still kind of hard to find because of all the damaging radiation that can lead to their destruction. But what if we can get below that and we can access either areas where perhaps even there is enough subsurface water that there is current life refuges, or at least better preserved evidence of extinct life. So that's one thing that we'll be looking forward to, again, is sort of moving below just that thin surface layer. Other things we've learned about Mars just in the last several decades of exploration, of course, we know that there are water caps on Mars in addition to CO2 caps. These are places that we've talked about could be useful for ISRU, but of course there's certainly potential places that we might want to look for life, places where the subsurface water is likely a lot closer to the surface and more persistent and more continuous. Even with the Phoenix lander, we're able to see some of that water close to the surface. We have imaged the surface enough again to find a lot of evidence of past flowing water, and these, again, are locations where we might find, with the right types of mineralogies and other conditions, that might be more promising. I think we've learned a lot more about where to sort of look for the evidence to get at our big driving question. And then, of course, the recurring slope lineae, the RSL, we've seen some, I don't have such a good video as Jim does, some great videos of this. We can see Mars is an active planet, for sure. We're seeing these changes. We're seeing the effect. Is it subsurface water that's coming up? If so, that's a place, that we're certainly eager to go. But I had to put this caveat. We had the great presentation earlier by John Rummel about planetary protection, and of course this is just coming from the science point of view, is that we want to make sure that when we go looking for life, that we're very, very careful about what it is that we think we're detecting. And so when we want to go to the places that are most likely to have it, but that's the added challenge, of course, of those are the places where you're more likely to bring forward some kind of contamination or something that will script your signal. So that's something really important that we're always thinking about as we move forward. The other thing that we have heard a little bit about, and that we've learned so much more about, that's helping in our understanding of how to explore Mars, is just how prevalent life is on our own planet. Pretty much, it seems like every nook and cranny that you look at, we can find some kind of life. And we can find life in environments that have a lot of similarities, that are very extreme, but have overlap with the kinds of places that we have found on Mars. And that gives us a lot of information on trying to understand, well, what are these limits of life? And what types of ecologies and communities do you have or do you need, and what types of environmental parameters need to be present to support life or to have supported, for example, life in the past. So I just have some pictures up here. For example, the Atacama Desert, which is the driest place on Earth, down in Chile, really high. It has a lot of similarities with the Mars surface, or really dry regions on the Mars surface. Yet, if you go there, you'll be able to find microbes and ecological systems in niches that can survive on very brief periods of humidity. Places in Antarctica and the dry valleys, down in the bottom left at, interfaces that we might find on Mars, interfaces between ice caps and soil, places such as maybe these buried glaciers that we've seen, places like that where there might be life located. I've put in a picture for Dr. Boston from some of the caves. Deep underground in these caves that are full of these volcanic nasty gases. There's life there, and it's thriving, and it's amazing. And especially when we think about, again, on Mars itself, it may be that the places that life has been retreated to over time would be in some of these smaller locations. And if we have a better understanding of what those characteristics are and what those properties are, can guide us in our searching for that. We've also got some really nasty type sulfuric spring areas. We know that there was a period on Mars where there went through a whole sulfate, really acidic sulfur water period, but life certainly could have adapted and thrived through some of that. And of course, the Chernobyl gives us an example of the type of radiation resistance that life can have when we think about the radiation conditions on the Mars surface or in the Mars subsurface. This is again, not necessarily going to be a deal breaker for certain kinds of life. So with all of these lessons that we're learning by sort of peeking over every rock and going into every cave on Earth, it's giving us a lot more information of what to look for, where to look when we're exploring Mars. Okay, so to draw on my most personal experience, I wanted to talk back again to some of the lessons that we've learned from Curiosity, where we have gone specifically, to understand, again, looking back 3 billion years, we have an idea what was going on Earth, what was going on Mars. Is it possible that the planet was habitable at that time? And so here we've interrogated one local region on Mars, and we heard some great results earlier from Dr. Mahaffey, but I'll just review some of them and how, again, just like with Viking, it was said earlier, we land, we go to find out the answer to a question, we get 100 more questions, right? And the same thing is going to happen every time that we go back. It's just the nature of exploration. And so, for example, we went to this location on Mars. We knew we would be accessing this period of Mars history that seemed promising for the kind of conditions that we're looking for. And we did find in this region, Yellowknife Bay, certainly a lot of the elements that we would think of as being necessary for habitability. Again, not necessarily looking for life, but just looking for an environment that could support life. And we did find what looked like an ancient lake, sediments from an ancient lake that had been there, had been persistent water. It was around a neutral pH, not extraordinarily acidic like some of the previous environments that we found before, things such as low salinity. Again, a place looking kind of friendly for life to hang out. Someone said maybe you could drink it. Looking for the types of elements or the nutrients that we know life needs. So sort of the SHNOPs, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. We found all of those elements in this environment, sort of preserved in the rocks. And this is kind of a cool one, because I know earlier we heard from Dr. Levine that it was really exciting for Viking to find nitrogen in the atmosphere of Mars. That was an exciting finding because nitrogen, we know, is so important for life. However, molecular nitrogen in the triple N2 bond isn't really as useful for life to be using. It's also important for it to be available sort of in a more activated form in the environment, to be bioavailable. And with Curiosity, what we were able to find is nitrates in the soil. So a form of nitrogen in these nitrogen-oxygen anions, which is, we know, can be metabolized by life, can be useful for life on Mars. And same thing with some of the other elements, not just that they're there, but they were found to be there in forms that could have been available for life in that environment. But then, of course, the next question, would be, but were they really, what state was all of the carbon in? What state was the hydrogen in, for example? The organic molecules one, that's a big one, and I've just shown the chlorinated organics that were in that one paper from last year, but we got to see earlier that I didn't know if I should show it yet, but PI prerogative. Paul showed some more of the organics. that don't have chlorine in them. They're not all chlorinate. We found some with some sulfate in them. We have evidence for other larger organic systems. And then that just leads us to more questions. So we know that organics are delivered by meteorites. Are these the remnants from those types of organics that have been processed by surface chemistry or by radiation on the surface? And are we seeing the product of that deposition from an earlier time? Or were these molecules from larger molecules that were involved in some kind of prebiotic system and then processed by surface chemistry or surface radiation after burial? And that's what we're seeing. And so to try to go and backtrack and get the answers that's something that curiosity can continue to do, but then certainly as we go back with Mars 2020 and we're able to collect that samples, and then we'll have a new interrogation tool. We'll be able to look for the biosignatures and look for some of these organics in the mineral context before sort of digesting up that sample and see what that can tell us perhaps about the origin. And then back to the drilling, again, if we're able to drill deeper, will we find different products that haven't been exposed to radiation, and will we learn more about the sources of those organics? Because again, we know there's organics everywhere. We can see them in meteorites. So the question is, how intimately involved of a carbon cycle could there have been on Mars or on ancient Mars? So those are just some examples kind of looking forward. I'm being a little agnostic as to whether we're going to answer all these questions with robotic explorers, with human exploration, or with a combination. If we have humans, on the moon and low latency telerobotics, I think it's going to be a combination of all these things, sample return as well. But I wanted to end just on this photo, this view of Mars that came to us first from Viking. Thanks to the Viking mission and many of the people in this room and your wonderful accomplishments, this is the Mars that I grew up with. And even though there's no plants in this picture or obvious signs of life, this was still a huge inspiration to me and many of the other people in this room and other scientists I work on at wanting to explore Mars and wanting to learn more about the solar system and the universe around us. And one thing I also just wanted to say is that looking forward, I think that we've got, again, an amazing future enabled by all of this fantastic technology. We have all of these wonderful science questions. And I think there's really just not an end to our curiosity about the planet next door to us. Every mission brings us with some awesome new information, but again, more questions that are going to keep us going back. And I also wanted to reflect back on something that Dr. Bosson said earlier, and looking back to Viking and looking forward ahead of us, another thing that I think is important and that I'm struck with is that while, whether it's as the community or the nation or really the world, we may be less naive about how easy it will be to find life on Mars, but we are still ever hopeful. And I don't think that any of the exploration so far has been discouraging in that respect whatsoever. We're still very excited to keep going. So, thank you.
Thank you, Melissa. We have a few minutes left for questions, so we're going to open up the floor. We have a microphone. If you want to come to the microphone and ask your question so the folks online can see, please step up. We've got a couple. Can you come up to the microphone over here? Another fresh young face from the Mars exploration community.
Are we able to get to Mars before an asteroid will hit Earth and wipe out people?
All right. Who's going to take that one?
So I'll answer that, and it's unequivocally yes. Yes, we'll get to Mars before a disaster happens on Earth. But our plan actually is indeed to assess the near-Earth objects, what are the potentially hazardous ones, identify those, their characteristics, understand when those threats would be more obvious to us in terms of when in the future we may have impacts, and then do something about it. The one thing the dinosaurs didn't have was a space program. All right, and we do, and therefore we just need to keep a steady pace, making progress in each and every one of those areas. You know, when I look out and I see our parents, we wouldn't let our 2-year-old child run around in the street because we know what the dangers are. It was a matter of 50 years ago, we didn't know really what the dangers were of this planet in terms of the environment we are in. And now we do. It's through the study that's facilitated by NASA spacecraft, landers, orbiters, the things that we survey and understand, that we understand the environment that we're in far better than we ever have before. And we've got to keep that going. We've got to stay on that path. It's the only way we're going to understand how we as a species will survive into the future.
Next question, Norm Crable, another one of the Vikings.
Well, I've got 2 questions, but I'll throw the first one out. You're going to put boots on Mars. It's not clear to me how you're not going to contaminate Mars. If you've got people inside those boots, you're going to contaminate it.
Yes, we will contaminate Mars when we send humans. There is no doubt about that. And so the idea is to say, how can we do the best science that we can before we send humans? How can we make sure we're not contaminating Mars before we send humans? And then once humans are there, at least the initial plan will certainly be to keep them well away from what we term special regions. And those are these areas you've been hearing a lot about today, where we think there's potentially liquid water coming up from the subsurface, areas like glaciers or buried glaciers where there still could be extant life. And we will study. And I'm well aware the wind blows on Mars. It blows all the time. It distributes material all around the planet. We have to be very cautious about that. But on the other hand, we need humans on Mars to study Mars, to really understand the planet, its implications for life in the solar system. We need to get humans there, so we have to go into it with eyes wide open.
Norm, do you have a part B?
Well, I'm still doubtful. You could do in situ DNA analysis and not even have to bring the samples back.
Well, provided that the life that's there is DNA based. There's so many questions about what kind of life we're really looking for. So a critical element of that is bringing those samples back and studying them in a methodical way where we can control the environment that they've arrived back in, understand based on the analysis that we can do what those samples tell us, and indeed look for not only a past life but extant life that may be in the samples that we acquire and bring back. Sample return is our most critical thing in the next decade scientifically for us to be able to do and accomplish.
And you have to do that without contaminating it.
Correct. And that's non-trivial. But those are the technologies we need to invest in, implement, be deliberate and cognizant about those, and then assess how well we were able to accomplish our goals of keeping the contamination down to a level that we can measure, so that any other life that appears above that we can identify. So we have a lot to learn in that area. Planetary protection, by and large, is really coming of age now in this next decade. And it has to, and we need to embrace it and work hard with with these types of technologies and continue on. And Viking was the first group that took that on. They had methods to be able to heat the rover, heat the lander and at a temperature that would sterilize it. Unfortunately, today we have so many sensitive circuits and so many things that we actually can't do it that way. We have to find other techniques. And so we're doing that now. We're doing a variety of research in that area, and we'll be implementing those new techniques on 2020. But that's going to continue on for each and every one of the next series of missions.
Okay, I have my second question. You know, the trip time is really abominable. It's a real hazard. 8 months, whatever. There is a technology that has been being developed independently of NASA, plasma propulsion. And Franklin, what's his name?
Chang Diaz.
Says he can get you there in 39 days. Now, just for fun, I had an intern working for me do another study, accelerating at 1G halfway and flipping it around the other way, decelerating at 1G, 9.5 days. So you got artificial gravity. You've got, obviously you have to have a nuclear power source to do this, but you could create an electromagnetic field for a radiation shield. So is anything being done with plasma propulsion for humans?
Yeah, so actually, Human Exploration Operations Mission Director, Advanced Exploration Systems, as part of Next Step, actually, it was a different solicitation than the HABs, are funding 3, what I'm calling very high power electrical propulsion concepts. One of them is Franklin Chang Diaz concept. It's VASMIR. It's been around for a while. So there's this kind of argument. There's many technical challenges with very high power electric propulsion, but nothing is better than getting data. So it's through these 3 efforts, we are going to get runtime and data on these systems and ground test, and then we can evaluate the efficacy of them moving forward to reduce trip time. And then if say that system pans out, then we need a reactor, 1 megawatt or more, to drive it. And we are working on reactor technology as part of nuclear thermal propulsion that will then could be a power source for that type of drive system or another high power nuclear electric type drive system.
Well, I'm glad to hear about it because, you know, I thought it would be at least discussed in this meeting, but thank you for updating me.
Yeah, thanks for the question.
So we've got a couple of questions. I've got one that's risen to the top of our list on our crowdsourced tool here, so I'm going to ask it, and it looks like it's to all of the panel. How will the U.S. commercial industry be engaged in the future journey to Mars, and what about the internationals? And it looks like Greg is locked and loaded, ready to answer that.
Yeah, and the answer is they already are. We have, on the commercial side, partnerships with commercial entities for which we're buying today commercial resupply services to the space station from SpaceX and Orbital ATK. We're now taking the next step with Crew. We have a partnership with Boeing and SpaceX, and we hope to get the same place there. We will get the same place there, where we are buying crew transportation services from the commercial sector. And then we mentioned earlier the next step habitation. That's a step to get the private sector engaged in the habitation capability in both LEO and deep space. We also, somebody mentioned earlier, Red Dragon, where SpaceX wants to land a modified version of the Dragon capsule on Mars. That's being done in partnership with us. We're going to be providing the Spacecom and nav for that. We're going to be sharing data on the EDL associated with that. So, and then we're engaged with Blue Origin, who's developing engines that they want to be able to provide the engines for next generation launch vehicles. We're working with them under this same commercial agreement we started off with with SpaceX and Boeing and Orbital ATK. So across the board, we're working with the private sector at the rate that they want to go. It's a great symbiotic relationship because they can do things, some things faster than we can, and they can be a little bit more nimble. They can operate without the kind of scrutiny that the federal government can. On the other hand, we have a long history of technology development that they are drawing on in order to do their work, and then we can advance in areas where we can lead in deep space activity where they're not ready to make the investment. And so there's a great partnership going on there. Internationally, of course, the International Space Station is the showcase, the pathway for international collaboration in space. We are discussing with each of those partners their interest in being involved in cislunar space development, and operations. And then beyond the traditional space station partners, we always talk about those 4 engaged in ISS, but there are actually 90 different nations doing experiments on ISS today. And we are continually involved with those folks wanting to, as they want to expand their ambitions in space, they are coming along with us. They're looking to us to lead, they're looking to us to set the direction, but they want to come along with us. And so I think on both fronts, international and commercial, U.S. private sector, we're very much engaged, and we're all going to do this together because it's going to take all of us and all of the best of our intellects, the best of our resources, the best of our technological know-how to get humans to Mars. And so we'll be doing this together.
Mention a couple things from a scientific perspective. You know, even though we talk about, this is NASA's mission, this is ESA's mission, what we really should be talking about is they're in partnership. One agency is the lead, and the other nations contribute. 2020 is an example. We have the weather station on 2020 is built by the Spanish. Just exactly as they have built that for Curiosity. In addition to that, the French space agency, CNES, is working with our principal investigator on the SuperCam imager for 2020. In addition to that, we also have, as I mentioned, the ground-penetrating radar is being supplied by Norway. So each and every one of our missions, to sometimes a great extent or even a lesser extent, have international partnerships. That's really important for us, to really leverage the capabilities that other agencies and countries have developed. And from a scientific perspective, our scientists look at it as a community, and it's very international.
All right. Thank you very much. I think with that, we are out of time. I want to thank all of our panel members from our capstone panel session today. I want to thank the Vikings, all of those who were here today and presented, and all of those who contributed to the Viking mission. So thank you very much. This is all for you. So real quick, a couple more folks. I need to thank Joel Levine and Gus for helping us put this together. I think this was a great day and a great way to recognize the Viking mission. Thank you, gentlemen. And to Gail Langevin and Sasha Ellis for coordinating all of the logistics for this. So thank you very much, everybody.